Hi, welcome to Sunil Maths tutorial, Galois Theory, class number 10. Let us see the first definition, minimal polynomial. A polynomial is said to be minimal if it satisfies two properties. The first property, it must be monic, and the second property, it must be irreducible. Monic means leading coefficient is 1. Irreducible means it has no roots in the defined field. So, right, a monic and irreducible polynomial, is called minimal polynomial. That is the definition. Important one. A monic irreducible polynomial is called minimal polynomial. Here I give two examples. X square plus 1 over capital R is minimal. X square minus 2 over capital Q is minimal. So, right. The next definition, algebraic extension. In the previous class, we learned about algebraic element. Suppose capital E is an extension field of the field capital F, and an element alpha belongs to capital E is said to be algebraic over the field capital F if there exist scalars a0, a1, a2, and so on an, which are not all zero in capital F, such that a0 plus a1 alpha plus a2 alpha square plus and so on plus an alpha power n is equals to 0. This is nothing but algebraic element. An element is called algebraic if this condition holds. If every element of capital E is algebraic over capital F. Then capital E is called algebraic extension of capital F. Very, very important definition. Remember that. Every element of capital E is algebraic over capital F, then this extension field E is called algebraic extension. That's it. Next, we are going to prove a theorem. Let us see the statement of that theorem. If capital E is a finite extension, of the field capital F, here it is the statement. Please observe that. If capital E is a finite extension of the field capital F, then E is algebraic extension of capital F. It means, simply we say that every finite extension is algebraic. It means every finite extension is algebraic. That's it. Let us prove this theorem. Let capital E be the extension field of capital F, and define the dimension of E over F is equals to n. The dimension of E over F is equals to n, where this n is finite. We have to prove that capital E is algebraic over capital F, or algebraic extension of capital F. Both are same. So, right, to prove that, let us take an element alpha belongs to capital E. Since E is field, then obviously 1, alpha square, and so on, alpha power n, 1, alpha square, and so on, alpha power n. These are elements corresponding to the element alpha. Now consider a set with these elements. Now consider a set capital S having all these elements 1 alpha, alpha square and so on alpha power n. Here you clearly observe that number of elements in S is equals to n plus 1. Number of elements in S is equals to n plus 1. And remember that the dimension of E over F is equals to n. The dimension of E over F is equals to n means every basis of E having n elements only. Every basis of events having only n elements. It means, what it means? Every linearly independent set can have n or less than n elements. It means if a set having n plus 1 elements must be linearly dependent. This is the point you have to understand here. I repeat the steps, please observe that. Here the dimension of E over F is equals to n. It means the basis of E contains n elements only. It means every linearly independent set defined over capital E can have only n elements or less than n elements. And you can apply the same thing to our set capital S having n plus 1 elements. It means this S is linearly dependent. If this S is linearly dependent, by applying the definition of linearly dependent set, there exists some scalars a0, a1, a2, and so on an in capital F. I am writing the definition of linearly dependent, not all zero, such that a0 plus a1 alpha plus a2 alpha square plus and so on plus an alpha power n is equals to 0. Here alpha belongs to capital E, and satisfying this definition, it means what it means? This is nothing but the definition of a algebraic element. This condition shows us the element alpha is algebraic over capital F. The element alpha is algebraic over capital F. You can apply the same theory for every element. We choose arbitrarily an element alpha belongs to capital E. We prove that the same alpha is algebraic over capital F. Therefore, we conclude that every element of capital E is algebraic over capital F. If every element of capital E is algebraic over the field capital F, then what it means? Capital E is algebraic over capital F. Therefore, we conclude that every finite extension is algebraic. Algebraic extension. That's it. This completes the proof of our theorem. Here remember that we defined two very important definitions. One is the minimal polynomial. The second one is algebraic extension. Minimal polynomial means a monic and irreducible polynomial. Algebraic extension means every element of E is algebraic over the particular field. That's it. Now we are going to prove one more theorem. Right. Let us see the statement of that theorem. Let capital E is an extension of F and U belongs to E is algebraic over capital F, then F of U is algebraic extension of F. Simple theorem. Very simple theorem. Let us prove one by one, step by step. Given that capital E is an extension of F, and we choose an element alpha u belongs to E is algebraic over capital F. The element u is algebraic over capital F. Apply the definition of algebraic. If u is algebraic over capital F, then there exists a polynomial p of x belongs to capital F of x. You can write monic and irreducible, or simply a polynomial p of x belongs to f of x, such that p of u is equals to 0. Now assume that the degree of p of x is equals to n. If you assume that polynomial is monic and irreducible, then p of x becomes minimal polynomial of degree n such that p of u is equals to 0. That p of x becomes irreducible polynomial. So if it becomes irreducible polynomial, then obviously f of u is the subfield of E generated by f and u. F of u is the subfield of E generated by f and u. So f of u is the subfield of E containing f and u, and degree of p of x is equals to n. It means the element u cannot satisfy any polynomial in capital F of x whose degree is less than n. This condition shows us there must be a set 1 comma u square and so on u power n minus 1 be a basis for the subfield f of u. Now it follows that if it is a basis, it contains only n elements. So dimension of f of u over f is equals to degree of p of x. This is nothing but n. Therefore, dimension of f of u over f is equals to n means where that n is a finite number. In the previous theorem, we learned that every finite extension is an algebraic extension. So obviously, f of u is an algebraic extension of f. That is the required condition also. Simple and easy theorem. Now we are going to prove one more theorem. This is also very simple and easy. Let us see. Let capital E be an extension. Let us take capital E be an extension field of capital K. And K is a subset of E consisting of all elements that are algebraic over capital F. It means capital K is the set of all algebraic elements over capital F. These algebraic elements are taken from E. We are choosing the algebraic elements from capital E and we notate them as K. And the statement is then K is subfield of E and algebraic extension of F. Then K is subfield of E as well as algebraic extension of capital F. Again, simple proof. Let capital E is an extension field of capital F and define capital K is the set of all algebraic elements of capital E over capital F. It means set of all elements alpha such that alpha belongs to E is algebraic over capital F. So right. Now we have to prove that. That is the point. We have to prove that this capital K is a subfield and subfield of E and algebraic extension of capital F. This is the statement of our theorem. E is an extension of F. And K is the set of all algebraic elements of E over F. That is alpha such that alpha belongs to E, which is algebraic over F, Our aim is to show that K is subfield of E as well as it is algebraic extension of capital F. So to prove this, yes, to prove this, let us take two elements from K. Let us take A comma B belongs to capital K. It means A comma B are algebraic over capital F. Then obviously F of A comma B be the subfield of capital E. I mean, actually E is extension of F, and we said that A comma B are algebraic over F. By previous theorem, there must be exist one midfield F of A comma B like this. F of A comma B is extension of F and E is extension of this field like that. Then F of A comma B is the subfield of capital E. F of A comma B is the subfield of capital E, and also this F of A comma B, is algebraic over capital F. So right, this F of E is a subfield of E and algebraic over capital F means, and also we said that A comma B belongs to F of A comma B. A comma B belongs to F of A comma B. Here please you observe that. F of A comma B belongs to F of A comma B, and since F of A comma B is a subfield, by the definition of subfield, A plus B and AB inverse both belongs to F of A comma B. If AB inverse and A plus B both belongs to F of A comma B, it means you can conclude that these two elements A plus B and AB inverse are algebraic over capital F. Already we said that capital K is the set of all algebraic elements. Therefore, this A plus B comma AB inverse belongs to capital K. Remember that these two are the I mean A comma B belongs to K implies A plus B belongs to K and AB inverse belongs to capital K. This is the necessary and sufficient condition for a set to be a subfield. This is necessary and sufficient condition for a set to be a subfield. Therefore, capital K is subfield of capital E. As well as it is algebraic over capital F. This completes the proof of our theorem.